This is my video on Le-Chatelier's principle. So for this page, what it says is fill in all blanks with either up, down, left, or right arrows or possibility of no change. And I give you the equation here. And the equation is CH4, which is methane, plus 2H2S goes to CS2 and 4H2. And they're all gases. And I give you the delta H as a positive 232.4 kilojoules per mole. So the first thing I want to do is look at the delta H and figure out where the heat term goes, if it's a reactant or a product. And since delta H is positive, and to be honest, it doesn't really matter what the number is right now, just looking at the sign, delta H is positive, so this is an endothermic reaction, and heat is a reactant. So I'm just going to write heat there. And I'm going to start to fill this out. So we have heat, we have the concentration of CH4, the concentration of H2S, we have CS2, and we have H2. Now this reaction is in equilibrium. So what that means is that the rate of the forward reaction, and the forward reaction is where the arrow is pointing to the right, it's basically the one forming products, is equal to the rate of the reverse reaction. The reverse reaction is the one that points to the left, which is where reactants are remade. So those two rates are equal, which means the concentrations of these substances is not changing when it's at equilibrium. It doesn't mean nothing's going on, it just means that the rates of the forward and reverse reactions are equal, so the concentrations are equal. So what happens in Le-Chatelier's principle, if you add some kind of stress, and that's what's in this left-hand column here, a disturbance, to that system that is in equilibrium, it has a tendency to reestablish a new equilibrium. And the way it does that is by either shifting to the forward reaction, basically shifting to the right, making more products, or an increase in the reverse reaction, which would cause a higher concentration of the reactants to form. So what we want to do is figure that stuff out. Now the way I have this set up, I'm going to put a line here to designate between the reactants and products, because that will make that a little easier. So when you're doing this, the first stress, the first disturbance we're going to look at, it says remove H2S. So the concentration of H2S is going to go down because you took some of that away. The reaction, the system is going to have a tendency to reform some of that H2S that it lost. So if it wants to reform H2S, the way it does that is by consuming or sacrificing some of these products. The CS2 and the H2 react more to reproduce some of the reactants. So the reactants are going to go up and the products are going to go down. And what happens is this is a shift to the left. Now there's different ways you can think about this, and it doesn't really matter which order you go in, whatever makes more sense to you. I'm just going to erase some of this for this first one. So if we start off with removing H2S, sometimes people like to think of it as if you took something away, the equilibrium is going to shift towards whatever you took away. So since we took away a reactant, the equilibrium shifts towards the reactant side because it wants to remake that. So everything on that side is going to go up, so the CH4 and the heat, because if you remake one reactant, you end up remaking the other reactants. You can't just make one. And the way it does it is by using up some of the product. They get consumed. If you increase the pressure, now when you think of pressure, you want to look at two things. You want to make sure they're gases, and each of these is a gas. And you also want to look at the coefficients, and this equation is balanced already. So in terms of coefficients, we have a total of 3 moles of gas on the left and a total of 5 moles of gas on the right. So when you increase the pressure, it's like saying you caused more collisions to happen. The reaction is going to try and minimize that disturbance, so it's going to shift to the side that would have less collisions. And 3 moles of gas will collide less with the walls of the container than 5 moles of gas will. So when you increase the pressure, when you cause more collisions, it's going to shift to the side that will result in less collision. So it's going to shift to the reactant side. So everything on the reactant side is going to go up. and the product side is going to go down. So again, the CS2 and the 4H2, they are getting consumed. They're getting sacrificed to make more of the reactants. Now, sometimes people think about pressure in terms of volume, and it's one of those things, whatever works better for you. I tend to think about it as pressure, but if you want to think about increasing pressures, decreasing volume, and then going from there, so we'll shift to the side that will take up less space, whatever works for you. Increasing the temperature. Think about heat as if it was a chemical. You just increase the amount of heat. The reaction is going to try and minimize that disturbance, so it's going to consume some of that excess heat. It's going to try and get rid of it. And if you look at what's going on in this reaction, the things that react with the heat are the methane and the H2S, the hydrogen sulfide gas. So what happens is, to get rid of that extra heat, it uses some of that methane and H2S to react with that excess heat. So their concentrations are going to go down. And what you're doing now is you're causing more interactions between these reactants. And when they interact more, that means you're going to form more products. So you're going to get more of the stuff on the right-hand side. So equilibrium is going to shift to the right. The other way you can think about this, if you prefer, when you add a substance, like adding heat, think about it as a substance, equilibrium is going to shift away from it. If you add CS2, right, so the first arrow I'm going to add is an up arrow in CS2. Think about what is the reaction going to do. What does it have a tendency to do? It was in equilibrium, you added CS2. It is going to try and minimize the disturbance that you just made. So it's going to consume some of that excess CS2. And again, look at what reacts with the CS2. The hydrogen gas does. So the hydrogen gas is going to get sacrificed to consume some of that extra CS2. Now you're increasing the interactions on the product side. So when these things interact more, they are going to reform the reactants. So their concentrations are going to go up. And reaction equilibrium is going to shift to the reactant side. Now again, if you add CS2, if you prefer to think about it this way, when you add something, equilibrium shifts to the opposite side. So once you add something on the product side, you could draw the arrow going to the left. It's going to shift away from it, and everything on the left is going to increase. All right, now we've removed methane, CH4. It wants to regain or remake some of that lost methane. So the way it would do that is by using up some of this product. The product gets consumed to make reactant. So it's going to shift to the left. The other reactants are going to go up. Now I leave the methane as a down arrow. And the reason why I do that is the reaction is never able to fully get back all of the CH4 that you took out. So you're going to be at a net loss for CH4, which is why I leave that as a down arrow. So that first arrow you put in, always leave it. So removing 4H2, for example. Well, we have a down arrow in the concentration of H2 column. So I'm going to leave that down arrow there. Now what the reaction is going to do is trying to remake that H2. It's never able to remake it all. So I keep it as a down arrow. And the way it makes product is by using up or consuming some of the reactants. So all of their concentrations go down. If you're making some H2, you're also going to make CS2 because you can't just make one product and not the other. So the CS2, the carbon disulfide concentration, that is going to go up. And what we're doing is shifting equilibrium to the right. Remember, the first thing we put in was this down arrow for 4H2. And if you take a substance away, it wants to remake it, or it's going to have a tendency to minimize that disturbance. So if you take something away, it shifts to the same side that that compound is on. So remember, it's all about minimizing the disturbance that was done.